this video, we're going to review everything that's going to be on your upcoming test in this radical and rational equations unit. So way back in the beginning of this unit, we started by looking at exponent rules, simplifying radicals, and looking at rational exponents. So to simplify exponent rules, you just got to remember about 7 or 8 rules, right? But the beauty of these problems is that it does not necessarily matter what order you go in. Okay, some things do matter, but there are so many different options. Whatever comes to mind first, roll with it. So if I'm looking at this example, I have a couple of negative exponents in there. I have parentheses and an exponent on the outside, and then I've got this fraction overall. I'm going to start by distributing this 3 because it's only on the top. And it goes to everything inside the parentheses, but only on the top. This 3 does not have anything to do with the denominator. So 2 to the third power is 2 times 2 times 2, which is 8. Now, if I have a variable with an exponent raised to an exponent, my rule says to multiply. So negative 2 times 3 is negative 6. Y cubed to the third power becomes y to the 9th. And z squared to the third power becomes z to the 6th. And then I'm just going to rewrite my denominator. From here, we have a couple different routes we can take. I'm going to simplify 8 over 4. to get 2, and then I'm going to subtract all of my exponents because that's my rule whenever I divide. Negative 6 minus negative 3. Anytime you have that double negative, it becomes plus, so negative 6 plus 3 is negative 3, so I have x to the negative third. 9 minus a 1 would be 8. And 6 minus a negative 2, I end up with another double negative, so it becomes 6 plus 2. So I get z to the positive 8. Now the only thing that I can't leave is this x to the negative 3. Everything else looks good. So my final answer becomes 2y to the 8th, z to the 8th, and then to make this negative 3 positive, I need to move it down. So I get over x cubed. Simplifying radicals, you have to make your factor tree, and I'm going to look for circles or for groups of 4 and circle them, right? Because that's what my index is. So 80, we have 8 and 10, then 4 and 2, and 2 and 2, and then the 10 breaks down to 2 and 5. Then I've got 2 x's and 6 y's. Looking for groups of 4, so I've got 4 2's, 4 y's, and that's all I can circle because I don't have enough of anything else. For everything you circle, you take 1 out. So I'm going to take out 1 2, 1 y. That leaves me with the 4th root. I didn't circle the 5, 2 x's, and 2 y's. And then I just multiply everything out. So I end up with 2y times the 4th root of 5x squared, y squared. And simplifying using rational exponents. Remember, with rational exponents, you've got to always think power over root. So if I rewrite 64 to the 2/3, that's the cube root of 64 squared. The cube root of 64 is 4. 4 squared, 16. And I'm done. We also talked about graphing square root functions. Remember our general form, we've got that a out front, and then h goes inside the radical with x, and a plus k on the outside. Our starting point is that hk point. That's a very important point on our graph. For this example, my hk point is negative 2, 1. So I'll go on my graph to negative 2, 1 and put a point. Next, I use my a value to determine which way it opens and if it's stretched or compressed. My a value is a positive 2, which means it opens up, and that 2 is going to stretch my graph. So I put a dotted line for a sketch of what my graph would look like if it were not stretched or compressed, and because I'm stretching it, my solid line is going to go up above it. Okay, domain for this graph, for any of the ones we do in our class, is going to be h to infinity. So in this case, negative 2 to infinity. And the range, because I'm going up forever, I'm going to positive infinity, so I'm going to be 1 to infinity. We also solved radical equations. Okay, remember the first thing you have to do is get the radical by itself. So for this example, the square root of 7x plus 14 minus 2 equals x. Square root of 7x plus 14 is my radical. I need to get that by itself, so I need to add 2 to both sides. So I end up with the square root of 7x plus 14 equals x plus 2. I can't combine those are not like terms. Now that my radical is by itself, I'm going to square both sides to cancel out that square root. Remember, you raise it to whatever power is your index. That cancels out the radical on this side, so I'm left with 7x plus 14 equals, this is a binomial, I got that addition in there, so I'm going to have to FOIL it. So I end up with x plus 2 times x plus 2. So first is x squared, outer is 2x, inner 2x, and last 4. Then I can combine those like terms, so I get x squared plus 4x plus 4. This is a quadratic, so to solve it, I'm going to set it equal to 0. So subtract 7x from both sides, subtract 14 from both sides, and get everything on one side. So now I've got 0 equals x squared minus 3x minus 10. This is factorable. I want to find two numbers that multiply to negative 10 but add to negative 3. And those two numbers are negative 5 and positive 2. And when I solve, I get x equals 5, x equals negative 2. I'm not done there. I've got to check for extraneous solutions. So I'm going to plug in both of my answers. So I end up with 7 times 5 plus 14, and then minus 2 has to equal 5. 7 times 5 is 35, plus 14 is 49. Square root of 49 is 7. 7 minus 2 is 5, and 5 equals 5. So that one works. Plug in negative 2. We got 7 times negative 2 plus 14 minus 2 should equal negative 2. 7 times 2 is negative 14. Negative 14 plus 14 is 0. Square root of 0 is 0, so I get negative 2 equals negative 2, which also works. So in this case, I have two solutions, and none of them are extraneous. Then we moved into solving rational equations. Okay, to solve a rational equation, I've got to find a common denominator with all of my fractions. Once I have the common denominator, I can cross it out and just solve my equation. I do have to check for extraneous solutions and make sure that I am not dividing by 0. So if I look at each of my denominators, the only value that would make any of them 0 is 0, because 0 squared is 0, 3 times 0 is 0, and 0 is 0. So x cannot be 0. I've got to keep that in mind when I go to solve this. To find my common denominator, I have to look for something that all of these denominators go into. So if I start with x squared does not go into 3x, and it does not go into x. But x goes into x squared, and x goes into 3x. So as long as I get something that these two go into, I have my common denominator. They both share an x, which means this one's going to need another x and this one's going to need a 3. So my common denominator is going to be 3x squared. To get x squared to 3x squared, I got to multiply top and bottom by 3. This 3x is just missing x, and the x is missing a 3x to get to 3x squared. Don't need the denominators anymore. So I have 3 times 1 is 3. Plus 3 times x, 3x, equals 2 times 3x, 6x. This is a linear equation, so I don't have to set it equal to 0. I just want to isolate x. I got to get x on the same side. So I'll subtract 3x. So I get 3 equals 3x, and then I just divide by 3. So x equals 1. I said 0 is the only thing x couldn't be, so x equals 1 works. And the last thing we looked at in this unit was variation. We had different types of variation. To start with, we had direct variation. So we have y equals k times x. Inverse variation, we said y equals k divided by x. So for example, you might say x equals 15 when y equals 10. And then you might want to find x when y equals 20. I'm not sure. If it were direct variation, all we would do is to find k is plug in that initial x and y. Alright, so you would say 10 equals k times 15. Alright, to find k, divide by 15. So then k equals 2/3. Your equation becomes y equals 2/3 x. You want to find x when y is 20, so we say 20 equals 2/3 x. I can times it by 3. 60 equals 2x, divide by 2. X equals 30. Okay, inverse variation means that I would do the same steps, but with this equation of dividing instead of multiplying. So I would say 10 equals k divided by 15, multiply by 15. K equals 150. Then I have y equals 150 divided by x. Plug in 20 for y, so I have 20 equals 150 divided by x. Multiply by x to get it out from the denominator, so 20x equals 150. Divide by 20, and we get x equals 7.5. I think. Yep. Okay. Joint variation is very, very similar to direct variation, but now we've got a z in there. So now we would say y equals kxz. So it's the same steps as before, but I've got that third variable in there. So we got to find find k, use k. Right? And then we looked at a couple of problems with combined, inverse, and direct. So it would say that a variable varies directly with another one and inversely with a third one. So we kind of merged our two equations together. And so we would say y varies directly with x and inversely with w, or whatever your variables are. So if you imagine looking just at the k over w, there's my inverse. K times x, there's my direct. We just merged them together to get one equation using all of them. Alright, direct and inverse variation, you have x and you have y. Or you have two variables, you plug them in, you find k, then you use k to find what's missing. Joint and combined, same idea, but you've got a third variable in there. You find k, you use k every time.